Hello, Historical Geology students. This is Dr. Hurt, and we're going to be continuing along today with another lecture, number 10, on Geologic Time. So you're going to have two lectures this week. This whole week's going to be Geologic Time, and hope you had a happy spring break. We're coming back from spring break now, and we're going to dive right into things again, so I hope you're ready. And it was kind of interesting now is that we've left behind all of our review over what's basically physical geography. It's physical geology. So those of you who have taken Geology 1303, physical geology, you might have noticed the semester so far in this class has been kind of review. We cover a lot of the same material, but now we're actually going to be getting on to material that is uniquely historical geology. So you're really going to be getting into like the nitty-gritty of this class, and we're basically starting our march through time pretty soon here. But right now we have to kind of settle out the basics, which is going to involve us getting very deep into the techniques of geology that we use to trace out geologic time and deep time. So here you go. There's a picture of Badlands National Park. It's in South Dakota. It's a pretty interesting looking place, right? And you can see that these stripes in the rocks are, I hope by this time you know, these are different beds of rocks, right? So you can see that a few things I want to point out. This is actually a really good picture for pointing out some what are called elements of stratigraphy here, principles of stratigraphy, I should say. So first of all, you notice that these flat beds that you see all over the place here. Whoops. Okay, all these flat beds you see here, right? In the red and the white. You'll notice for one thing, they're horizontal, right? They're horizontal. So beds of rock get laid down horizontally at first. We're gonna learn all these principles, which is kind of introducing them to you right now. So they get laid down horizontally at first, and sometimes they get tilted, sometimes they don't. Another aspect of this, you'll notice that they are continuous. They have what's called lateral continuity. So notice this bed of rock right here. Okay, I'm going to draw kind of a line sandwiching this bed of rock here. You can trace it with your eye all the way back here. And look, it goes all the way back there. And look, you can even see it back here, right? And probably like this bed right here. Look. Can you all see this like thick red bed? Okay. Notice how it's even all the way back here. So these beds are huge, right? They go laterally over huge areas. Okay, they cover it. And probably, we could probably trace some of these layers all the way back to these hills you see back behind us. So they go on they extend laterally for huge areas. Okay, so you're going to see that's a principle called lateral continuity. Okay, so I don't know if there's anything else I want to... Oh, you know what? One important thing I want to point out right here is... What do you think? Which of these beds do you think is oldest? This one, or this one? Well, this is the oldest bed. This is younger. And of those three, this is youngest. Okay, so that's another principle called superposition. So the oldest beds are on the bottom. Younger and subsequently younger beds are on top. Okay, so those are all very important principles of historical geology. It's called stratigraphy, that we're going to get into today. Okay, so we trace out the techniques and kind of our, I guess you could just call them techniques that we use to explore historical geology. And then we're going to be really getting into the march through time after that. So you have a few lectures coming up here, 2 lectures on geologic time and then another on what are called radiometric dating techniques, which are going to use radioactive isotopes to figure out the age of the Earth. Okay, so how old is the Earth? I hope by now you know that it's pretty dang old. In terms of when did it actually accrete together? The Earth basically finished accreting together. Of course, it's been slowly gaining mass. It gets a little bit bigger every year, just a little bit because as, meteorites and other things collide with it. But it accreted together mostly about 4.5 billion years ago. Okay, so just a reminder of some things here. So these are units that we use for time. right? And just remember, I know we covered this in like the first lecture or so, but you got to know these things, right? MYA equals millions of years ago. MA equals mega annum. It's the same as millions of years ago. So MYA equals MA. BYA is billions of years ago. GA is giga annum, means it's the same as billions of years ago. Sometimes you'll see things like KA or KYA. The K stands for kilo, and that, you might remember, means 1,000. So that would be 1,000 years. We're not going to start using Ka and kilo annum until we get to, like, you know, fairly recent times, okay? Because we're going to be talking a lot of this class. We're going to be talking about things that happened usually billions to hundreds of millions of years ago, okay? So just to kind of give you an idea of the depth of geologic time, because it's kind of hard to wrap your mind around it. This is a common exercise people use to help students understand things. But 4.5 billion years, suppose that we scaled down all of geologic time into 1 calendar year. Okay, so that means that Earth began, accreted together about 4.5 billion years, and that's going to stand for January 1st, right, the first day of the year. And then the present day right now is going to be December 31st, okay? So exactly 365 days. So if we scaled everything down that way, the moon was formed January 4th, right? So only 3 days after Earth came into existence. Okay, the first rocks that we have, the oldest rocks, represent a time of maybe January 24th. Okay, so that within the first month. The first evidence for life comes from, which is, we're going to get all into this about the first evidence for life, but that's around March 22nd, right? So just a few months. But the big evolutionary, what's kind of crazy is like the evolutionary Big Bang. So like we're going to learn all about this, right? It's called the Cambrian explosion, okay? That's when life really took off, because prior to the Cambrian explosion, animals were exceedingly simple. Most of it was just, animals were fairly new on the scene. And a lot of life, basically going from March 22nd, which represents 3.5 billion years, to 530 million years ago, which is 0.53 billion years ago. So for 3 billion years, life was little. I'm kind of drawing you what life looked like. Little gross. Oh, it disappeared because of that annoying thing. I hate that. It's like these little gross, paramecium. There's your little gross paramecium. Little single-celled organisms. Pond scum. That was life. That was all the life that there was on Earth for 3 billion years. And then after 3 billion years, we started getting animals. And then after animals, you see what animals have become. So you have all the way to humans, which are just a triumphant, magnificent creature. So and I'm not just saying that because I'm human. I mean, they really are amazing creatures. That there's never been a creature on Earth that is like humans. So they are unique and amazing. So but anyway, that all happened in relatively short time, right? No, by November 17th, you had the first, you just started really to get animals on Earth. And then dinosaurs, isn't this crazy? Dinosaurs went extinct around Christmas. And then right now, today, the present time would be December 31st. So, the dinosaurs went extinct not that long ago in terms of geologic time. Homo sapiens first appeared, like our species of people, like real people, they've been on the scene for basically 14 minutes. Okay, a very, very short time compared to the length of days that almost would appear to us almost infinite lengths of time, right? Your life, if you were lucky to live to 100 years, which you probably won't, your life lasts seconds, right? It's like just a few seconds. So it's, we experience a very, very small part. Human history sees a very small part of geologic time. So that's kind of an exercise to get your mind wrapped around geologic time, the depths of geologic time. So not even 1 second. Look at that. your life is not even 1 second. If we were to compress geologic time into 1 year, right? So we're mayflies, on the scene here. Time goes on very, very deep, very, very long. And you know what's crazy is that the universe existed, for many billions of years before Earth even came on the scene. So the universe is very old, right? Almost what would appear to us almost infinite stretches of time in almost infinite stretches of space as well. So there you go. There's your Christmas dinosaur. He died out on what would be Christmas Day, right? And now would be December 31st, right? So this is the time scale that we're going to use a lot in this class. And it's kind of like a pie chart, And you're going to see that we split up time. We learned this like in the first couple lectures. The Hadean is the first eon. We're going to have a whole lecture about the Hadean. We're going to have a couple lectures about the Archean, a couple lectures about the Proterozoic. And you can see what's kind of crazy is that the Hadean, Archean, and Proterozoic, they constitute the vast majority of time, geologic time, right? You can see that's like more than 75%. It's like 80 or 90% of geologic time. And, we're only going to cover these in maybe, like 2 weeks. We're going to cover all this information. So it's kind of crazy that, actually we're going to talk about like 90% of Earth's history in, like maybe 2 weeks. I think it's like 2 weeks. It's pretty crazy when you think about it that way. And the simple reason that we do that is just that we don't have that much information about these time periods. Okay, so there's just not many rocks and many fossils and stuff preserved from that time. We have a lot of information about the last 530 million years, and a lot happened in that time. A lot happened. We went from very simple animals, things like horseshoe crabs, trilobites, and stuff, all the way to humans in that time. So, pretty amazing. Now, just a little bit of history, actual human history, to kind of get us off the ground here and just give you some perspective on how geologic history and the study of geologic history has progressed through time, through human history, right? Through human ideas. So, the first person I can say who really was interested in kind of trying to nail down the age of the Earth was this gentleman here, James Ussher. So he was a primate of the Church of Ireland, and so he was a cleric, a priest, or I don't know, he'd be equivalent to a priest or a bishop, but not exactly familiar with hierarchy in the Church of Ireland. But a very famous work that he produced was this one. This is the Latin. Of course, he wrote it in Latin originally, but it means, the annals of the Old Testament deduced from the first origins of the world. And in this, he went out based on a lot of things, not just Holy Scripture, but a lot of historical documents and a lot of astronomical records. And he used those things, historical documents, the Old Testament, and the oldest manuscripts that were available and oldest data of astronomical observations available to try to figure out the age of the Earth. So, a lot of people like to make fun of this guy because he came up with an age of the Earth of only 6,000 years. And a lot of people like to make fun of that, and I don't make fun of it. I mean, I don't think it's right, of course, but I don't make fun of it because he was using the techniques, and he was using he didn't have radiometric dating and isotopes, and he didn't have a mass spectrometer. So it's not like he could have done, he went the pathway that he knew, which was through history and scholarship. And by the way, James Ussher was a tremendous scholar. I mean, this required a mastership of many different languages. He looked at Persian, Arabic documents and astronomical records. It required a command of many different languages and tremendous scholarship. So, I don't make fun of it. It was for its time, it was the best that they could do. But that's what they were going off of. They were going off of historical records. And actually, it kind of makes sense, because if you go off of history, well, what's the oldest historical documents we have? Well, there are thousands, maybe tens of thousands of years old, right? So it makes sense that you come up with an answer like that if you're going off of historical human records. A big advance to the study of geologic history came not too long after James Ussher. James Ussher died in 1656, and along came another actual, so this is Nicholas Steno, who is actually, he was also a cleric. He was a Catholic bishop. And by the way, it's also kind of interesting, he's actually a Catholic saint as well. So he's been beatified by the Catholic Church. So he was, a holy man on top of accomplished scholar. But this guy, Nicholas Steno, did a lot to advance the study of geologic history. So one thing that he realized, he did a lot of studies of fossils and rocks, and one thing that he found is that people were finding what appeared to be fossilized shark teeth and shells and marine organisms high in the Swiss Alps, right? So how did people explain that? Isn't that kind of weird, like, finding sharks, things that look like shark's teeth in the Swiss Alps? People didn't really have an explanation for it, and a lot of them just kind of thought it was coincidence. But he believed that these fossils were definitely preservations of ancient life, that they were preserved in the rocks, and that therefore water levels must have been high enough to submerge these mountains, right? Because if you're finding fossils here high up in the mountaintops, there must have been a change in sea level or a change in the land level. So he came to a lot of these different conclusions, that there must have been drastic sea level changes in Earth's history. There must have been drastic changes in the height of the rocks. And another thing that he explained that a lot of people did not understand is that people knew at this time that these fossils, like fossilized shark's teeth, were not made of bone. They knew that they were rock and not bone. And so people had a really hard time understanding that, because they're like, well, they look like shark's teeth, but you know what? They're not shark's teeth because they're not made of bone. They're made of rock. But Nicholas Steno was a very clever man, and he helped to explain how these fossils could be preserved through I hope you remember the process of mineralization that is able to convert the bone tissue into rock, solid rock tissue. Or not rock tissue, but solid rock, okay? So he showed how, Nicholas Steno, one of his big contributions, he showed how this process could happen. So before Steno, many scientists thought that fossils were formed in the rocks by inorganic processes, or that they fell from the sky, They didn't really know how this could have happened. But Steno's careful study, comparing those fossilized shark teeth with those of, living extant sharks. By the way, this word extant means still living. It's basically the opposite of extinct. So he proved that fossils were the fossilized remains of ancient life. Okay, and that had a lot of implications for things. It kind of suggested the world was much older than maybe just thousands of years, because these processes would have taken some time to accomplish. So Steno was able to explain why the composition of fossil teeth is not the same as that of living shark's teeth by this process of mineralization. Okay. Now, another huge contribution that Steno made, which we still use this today, it's still considered true. It's still something that, it's kind of amazing that 400 years ago he was able to understand these things. But he did a lot of studies of stratigraphy of rock layers, sedimentary rock layers. And he came up with what we now recognize as 4 laws of stratigraphy. So I'm going to go over these 4 laws. Sometimes we split them into 6 laws, sometimes 4 laws, but I'm going to go over these big important laws one by one. But right now I'm just going to kind of pass by them and just let you know that he figured out really these very important principles of stratigraphy. So we'll look at that. We'll look at that a little bit later. Next huge historical figure in historical geology was this gentleman. This is James Hutton. He was less of like a Renaissance figure and more of an Enlightenment figure. He wasn't a cleric like Steno and Ussher, and he was very much an Enlightenment thinker. And he came up with this idea that the processes that are happening, the geologic processes that are happening right now, are the same processes that have been operating in the past. And he called that idea uniformitarianism. So that the processes that are working now are uniform, the same, they remain the same as the processes that are working in the past. And what he realized is that processes like, erosion and deposition, that we can see they happen very slowly. And therefore, Earth must be very, very old, because in order to get mountains and valleys and erosion on the scale that we see it on Earth's surface, these processes, they work so slowly, Earth must be, millions of years old. He came up with this very, very famous phrase, no vestige of a beginning, no prospect of an end, And this was a time people were actually maybe starting to think that maybe there was no beginning to Earth's history. Now we know that's actually not true. It's a little bit too extreme. Now we know that there was a beginning to both the universe and to Earth itself. But they were starting with James Hutton to get a really serious view of the lengths of time that Earth must have been around. So, looking at these processes of weathering that we've talked about, weathering, transport, deposition, looking at how slowly these processes take place, he understood that Earth must be very, very old indeed, and he recognized, that the processes we see working today are the same ones that are working in the past. Molten lava from an active volcano, turns into fossilized, quote-unquote, fossilized lava beds that we find from the past, Ripple marks that we find in the shallow waters now are the same ripple marks that we find fossilized in the rocks, which I showed you pictures of these things, in the sedimentary rocks layer. So you should remember this term, uniformitarianism, and understand what it means. And it just generally means that the geologic processes that are operating today naturally, were operating over Earth's entire history. Okay, so geologic processes are very slow. They take millions of years, and so that Earth must be millions of years old rather than thousands of years old. Okay, so you can see that as we go from Usher to Steno to Hutton, people are starting to think that Earth is older and older and older. There was another gentleman I don't talk about specifically, but Lord Kelvin, who, based on thermodynamics and rates of cooling, concluded that Earth must have been about 20 million years old. So again, we're going up to tens of millions. Now, the current age that we get for Earth, which we recognize right now, the current estimate for the age of the Earth is 4.5 billion years, like I said. And that number kind of started with this gentleman here, which is fairly recent, 1956. So maybe from Enlightenment times, James Hutton's period, to fairly recently, 1950s, scientists were thinking that Earth was maybe millions of years old. But Claire Patterson came around in 1940s and 50s and suggested that actually, based on radiometric dating, we're going to have a whole lecture on radiometric dating, so I'm not going to go into much detail with it here, but based on radiometric dating, based on isotopes and the decay specifically of uranium to lead, that Earth must be pretty dang old. It must be around 4.5 billion years old, which was a pretty mind-boggling number, It's actually much older than what most people were thinking for the age of the Earth at that time. So anyway, that's where our current number comes from, So that's the concept of deep time. And of course, Earth's only a very small fraction of the total time, since time has existed, Time has only existed for 13.7 billion years in this universe, So what was, you can't add, people always like to ask, well, what was before that? Well, there was no before that, There wasn't time before that. There was timelessness. So you have to think of things existing outside of time, which is difficult to wrap your mind around, It's just the same thing with space, People say, what's on the other side of the edge of the universe? And the answer is nothing. There isn't space on the other side, because things can exist outside of space, things can exist outside of time. So whatever that is that exists outside of space and time, that's what there is, and in a sense, in that sense. So, but there was no, time began, as far as we understand, as far as we know, time began 13.7 billion years ago, and Earth's only existed 4.5 billion years ago. So let's talk about absolute ages versus relative ages. So relative dating, is something that we use a lot in geologic history, and as well as absolute dating. So we're going to talk about both these things: relative dating, absolute dating. So relative dating refers to when you know the sequence of events. Okay, and a lot of times, and for a long time in geology, James Hutton was basically the grandfather of geology, along with Nicholas Steno. I'd say a lot of times Nicholas Steno is recognized as the grandfather of geology as well. But they could only really date things, quote unquote, date things, and figure out ages in terms of relativity. So this strata, this layer of rock is older than this layer, right? This volcanic eruption happened after this volcanic eruption, or it happened after this bed of rock was laid down. Okay, so it's just figuring out ages relative to each other, right? Absolute dating is what we like, right? Absolute dating gives us actual ages for how old things are, right? So in terms of relative dating, if you were to look at this picture, this family photo, that grandma here on the bottom, I guess she'd be great-grandma, is the oldest, right? That grandma's next oldest, mom is second oldest, and then the daughter is the youngest, right? So that's relative dating, right? We know who's oldest and who's youngest. But absolute dating would be to know actually when grandma was born, right? So we don't actually know. I mean, we can guess, but we don't actually know how old grandma is in this picture, okay? So absolute dating would be actually we know, okay, grandma was born in 1929, grandma was born in 1951, mom was born in 1972, and the daughter was born in 1999, right? So that would be absolute dating. Okay, so when we want to figure out absolute ages versus relative ages, we're going to use different techniques. Relative time, we're going to use principles of stratigraphy. Okay, principles of stratigraphy are the principles that were all laid out and organized by Nicholas Steno. So we're going to figure out what layers of rock are older and what layers of rock are younger. Okay, and by the way, you're going to have some, I would say, pretty challenging exercises. They're going to be on the final, in which I'm going to show you pictures of rocks, not pictures, but like diagrams of rocks. And you're going to have to be able to tell me what is the sequence of events there are, And I'm not going to give you absolute ages. You're going to have to figure out the sequence of events based on principles of stratigraphy. So we're going to go through this, and hopefully it'll make sense to you. So, for example, we know that rocks on the bottom are older, generally speaking, than the rocks on top. Okay, the rocks on the bottom got laid down before the rocks on top. Okay, because things always get laid down horizontally, right? So things get laid down, deposited one on top of the other, almost like if you stack up a pile of newspapers or something like that. So hopefully you can look at this diagram, and I can just ask you, which layer do you think came first? So looking at this, which layer, of all these layers you see, which layer do you think came first? So hopefully you're thinking it's kind of like, hopefully you can see the different layers, and you can see that there appears to be a layer like this, right? So you can kind of see a layer jutting out like this, and whatever all this is, this seems to be the first layer that got laid down, right? Because it's on the bottom. Okay, that's called the principle of superposition. The oldest stuff is on the bottom. Okay, so let's start going through Nicholas Steno's geologic stratigraphic principles. Sometimes people split these into 4 principles, sometimes 6, so don't get thrown off by that. Sometimes I'll refer to there being 4, sometimes 6. Like right here, I have it as 6, which is fine. Okay, so the first principle is this. It's called original horizontality. So original horizontality, that principle states that when sediments are deposited, remember that sedimentary rocks are just collections of sediments, right, that got lithified through diagenesis. So I hope you remember all those terms. All those terms are going to be on the test. Diagenesis, lithification, etc., etc. So sediments get laid down. You know, for example, here's sediments in a tidal area. They all got laid down. You'll notice that they get laid down horizontally, right? They get laid down in a basin horizontally. So when we find rocks in the stratigraphic sequences, right, they're laid down in these horizontal layers. So originally, now the reason it's called original horizontality is because that's how they are laid down originally. Sometimes you'll find tilted beds, and the tilted beds mean that those layers got originally, they weren't deposited that way, right? The sedimentary rocks originally were deposited horizontally, but something happened that tilted them. Okay. All right. Now another principle here is superposition. So in superposition, it says that the oldest material is on the bottom, generally speaking. So when you see all these beautiful rock layers here, it's a mind-boggling. You know, look at all these rock layers. Each one of those layers represents thousands and thousands. You know, probably 100,000 years, right? And you can just see there's tons of them, right? So these rocks are laid down horizontally. The oldest ones are on the bottom, and so that's what superposition says, that the oldest stuff gets laid down first, followed by younger, progressively younger and younger stuff. So the youngest sediments are up here, right? This is the young stuff. This is the old stuff, right? And think of, like, for example, like professors that keep exams. I think it's kind of a funny picture. You know, I know how they're talking. You keep old exams, old student exams. You know, the oldest stuff is on the bottom, and you just keep piling it up and piling it up and piling it up, right? And the youngest exams are there on top. Okay, so that's called superposition. Now, another thing that's kind of hard, I think one of the harder things to understand, although I don't know why, but it's just kind of, I don't know, it doesn't make sense all the time when you're first starting out, but it took me a long time to kind of wrap my mind around it, right? But the next principle of stratigraphy is called lateral continuity. So lateral continuity means that when you find a layer of rock, okay, so you find these rocks here, right? You find this outcrop. These rocks don't just exist here. Okay, they are spread out over huge areas, okay? Because when deposition occurs, deposition generally occurs over regionally sized area, massively big areas. So look at this panoramic view of the Grand Canyon. Okay, you can see this layer of rock here. You see the contact, the light-colored rock and the red-colored rock here. Here's the contact between them, right? And it goes on and 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 on. And actually, by the way, you can find rocks in the Grand Canyon that are in California. Yeah. The Grand Canyon's in Arizona, right? But you find the same rocks in other places in California. Okay? These rocks were deposited over vast areas. So I'm just trying to tell you that, like, rock units like this aren't just little local things. It's not like, okay, I found a shale here in and it's going to just disappear. It only exists in Corpus Christi, and it's going to disappear if you go outside Corpus Christi. No, these things get deposited over huge areas. Now, think about the beach. Think about the Gulf of Mexico, and think about the beach. Think about all the sand getting deposited at the beach, right? That sand goes on. I mean, you could walk all the way along the coast, the whole Gulf of Mexico, all the way to Florida. And you could walk along the beach, and it's going to be sand, 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 sand for hundreds and hundreds, thousands of miles, okay? So that sand was deposited over a vast, vast area, okay? So expect beds of rock to continue laterally for vast areas, not just small areas, okay? So that's what lateral continuity means. The next principle is called cross-cutting, okay? And all it states, very simply, is that in order for if rocks are cut by something or intruded by something, okay, that the rock had to be there before it got cut. Does that make sense? It's kind of funny. I know it seems kind of funny and obvious in a way, but the rocks had to be there before they got cut. So, for example, here is, a white rock, a white country rock, sedimentary rock, that got cut by a basaltic dike. These are basaltic dikes, right? They're these little, kind of lines or planar features of basalt that got intruded into the country rock, okay? Well, that rock had to be there before it got intruded, right? So that means that the basalt is younger than the white country rock here. Similar with folding, right? So you can see the rocks here are folded. Now, again, horizontality, original horizontality. These layers got laid down horizontally at first, right? They're totally horizontal, but then they got folded after the fact, right? So you know that the folding had to happen after the rocks were laid down. Okay. Just some other things. Sometimes it's not clear. Kind of like what, is this a sedimentary, like for example, is this a sedimentary layer? Is it an intrusion? Is it a basaltic dike? I just kind of want to point out, do you see the area of darkness surrounding this thing? So that's a baked contact. Remember when we talked about, I hope you remember, we talked about metamorphic rocks. I mentioned hornfells and contact metamorphism. So, the contact metamorphism, the hornfells must have formed with the intrusion of this lava basalt dike, okay? So another important thing is inclusions of rock. So sometimes you will find, for example, pieces of basalt. Imagine this. What if you found pieces of basalt in this sedimentary rock that was above it? Okay? That would mean that the basalt dike must have existed before that sedimentary rock formed. Okay, does that make sense? So that's what inclusions refers to. Okay, baked contacts just means that when you find a hornfels rock or a metamorphosed rock, that it must have been, that rock, that protolith must have existed prior to the metamorphism. Which, it seems obvious, but you'd be surprised how complicated it can be to unravel all of these time relationships. Okay, so Steno's principles for determining relative ages. So I'm just going to kind of walk you through. I just want to kind of walk you through, this is something you're going to have on your test. Is I'm going to give you a diagram of a geologic cross section. So this is a cross section. It's just a diagram of a cross section, right? I'm going to just kind of show you how this would change over time and how you get the final result. Okay, so it'll make sense as we go along. So let's imagine that the first thing that happens is you have an ocean and it deposits all of these rock layers. Okay, so it deposits all those rock layers. The oldest ones are on the bottom. The youngest ones are on top. Okay. Now, at some point, the water dries up. Maybe this whole area gets uplifted. There's no more water. Deposition stops. Okay, so deposition stops. Usually when things are covered with water like this, deposition is active. You're actively depositing sand and silt and materials. Okay, but sometimes tectonic uplift occurs. It raises this whole area above water level. Sometimes water levels drop, but for whatever reason, the column is exposed now to weathering and exposed to the elements, and it's going to start to erode. So the next thing that happens is the intrusion of a sill. So a sill is it's a kind of a planar intrusion of magma that is horizontal and it goes along the bedding plane. So that's the sill. Okay, so that happens. That's the second event. Third event is folding. So you can see here that sill is now slightly folded due to compression. Okay, so let's say there's some tectonic event that compresses it. That sill is now you can see this folded sill. Then magma intrudes the folded sill and sediments. Okay, so you can see how the magma is cross-cutting. It's cross-cutting all of the. It's cross-cutting the sill. It's cross-cutting all the sediment. So we know that the magma must have come after the formation of the sill and after the formation of sediment layers 1, 2, 3, 4, and even 5. We don't necessarily, well, here's a question. do we know that the magma formed after the deposition of 6, 7, and 8? And the answer is we do know, because we can see that 1, 2, 3, 4, 5, 6, 7, 8 depositional layers were folded. They were all folded. And we can see that the folding event happened after the sill, happened after deposition, and we can see that the magma intruded after the folding event. We can tell that this magma body is not folded. So we know that, granted that's obvious to you that this magma body is not folded, we can tell that this has to happen after the folding. Therefore, this magma body is younger than 1 through 8. Okay. Now imagine a fault occurs. It offsets all of the sedimentary layers. It breaks the pluton, the magma plutonic body. We know that the fault must have happened after the pluton formed because it's cutting the pluton, it's cutting the sill, it's cutting all of the sedimentary layers. And then imagine a final insult. There is a dike intrusion. Okay, so you'll notice that the dike cuts the fault, and the fault did not offset the dike, right? So because if the dike had formed before the fault, the dike would have been offset, so it would have been cut. So maybe the dike would have been here, but it continued along over this way. Okay, but that didn't happen, right? The dike cut the fault. Okay, so what would happen in a test is I would give you something like this, something similar to this, and you would have to tell me, what are the different relative ages of the different events that you see that have occurred here. Okay, so again, you see the limestone, the shale, the sandstone, limestone, and then you see a sill here, right? All these things. You see the basalt dike, the fault, the granite intrusion. You're going to have to tell me the order that all these things happened in. And I just worked all this stuff out for you. So this is basically a depiction of this same thing, right? So anyway, that's what you're going to have to be able to do. One thing I wanted to point out to you here are these inclusions, okay? So you see they're the inclusions of sandstone, right? So that means that it shows you that this sandstone existed before the granite pluton existed, because there's inclusions of the sandstone in the granite pluton. Another thing, also notice this baked zone. Do you see this kind of reddish baked zone? Okay, y'all see that? That indicates that, that's probably now a Hornfels rock. It's a contact metamorphism rock, and it must have existed before the granite pluton was there. Okay, I mean the sedimentary rock layers must have existed before the granite thing was there. Another thing I want to point out, some people might think that this sill right here, that maybe it came before the sandstone, right? Because it's under the sandstone. So according to superposition, you might have thought, oh, it's under the sandstone, therefore it must be older than the sandstone. However, look at the inclusions of sandstone in the basaltic sill. That shows you that the basaltic sill came after the sandstone. Okay. So anyway, I know that's complicated. It's kind of funny you start off with these relatively simple principles, but when you put a big, geologic cross-section together like this, it's really complicated. And so, I give you some practice on the lecture assignment on this. I can't remember if it's on the first lecture assignment that you start off with or if it's on the second one, but you'll have some practice with this. And, gosh, guys, really take this seriously. This is worth a lot of points on the final. And, it really kills students. So make sure that you can do this. It's not something to skip over. I notice a lot of times on the lecture assignments when I assign this, people see it and they're like, this is hard, and they skip it, and then it comes back to haunt them on the final, and it really hammers them. So it's, I think on the final it's worth like 10 points or something like that. It's like a 10-point question or 7-point question. It's worth a lot. So anyway, you gotta know this stuff. You gotta be able to do this. All right, so let's just kind of examine. We're almost done here for today, but I want to kind of throw fossils into the mix in this whole idea of relative dating. So fossils can help us big time determine the age of a rock. And actually the geologic time scale that we are learning and have learned, it's all based on fossils. Okay, so all the different demarcations that we set up in the geologic time scale are based on different fossils. So remember that fossils are the remains of past life recorded in the rocks. Okay, could be anything from a fossilized skeleton of an animal. Okay, so where the bone tissue has actually been replaced with mineral content. Okay, so for example, the Smilodon saber-toothed tiger, right, this is no longer bone. Or actually, you know what? I think actually this is bone. This one is bone. Yeah, this one actually is bone. It was preserved in the tar pits, La Brea tar pits in California. It's a really cool. I lived really close to the La Brea tar pits when I grew up, so I used to visit this museum. It's a really neat museum. If you ever get a chance to, if you're ever in Southern California, I highly recommend visiting it. It's worth your time. Here's an insect embedded in amber, right? Here's petrified wood, where the wood actually got replaced with rock mineral tissue. Here's a basically what was a flash frozen baby mammoth, right? 37,000-year-old baby mammoth. So anyway, these are all types of fossils. Okay, so these are all types of fossils. It's just remains of past life preserved in the rock. Okay. Also, you get what are called trace fossils, which are traces of past life, not the actual bodies of animals or life, but just traces that they have left behind. For example, footprints. But it could be a lot of different things. Sometimes it's like fossilized burrows, fossilized tracks or pathways, kind of or dug out by different animals. So could be a lot of different things. So here's a question. Let's say that we date relative ages, we date all these different rocks all around the world. How do we know? The question is, how do we know? We might be able to look at a rock record and say, like, okay, like we can look at this, right, and be like, okay, sure, I got you. So this limestone is older than this sandstone, and it's the sandstone is older than this sandstone, and I got it. Okay. But how do we figure out, let's say we find, like, how do we know the age of this limestone compared to another rock on the other side of the world? Like, let's say this is this particular outcrop represents an outcrop in Texas. And let's say there's another outcrop in Siberia. How do we know the age of this compared to the age of the outcrop in Siberia? Because they're totally different rocks. Because totally different things are happening in different places. Like, and you can look at around the world right now. Like, okay, in Louisiana, there are swamps that are currently depositing coal beds. There are deserts in California. In Michigan, there are there's snowbanks, and there's different things, different weather. It's producing different rocks, right? Different sedimentary depositional environments. So how do we know in different depositional environments, like how do we know the age of? We know that these coal beds in Louisiana are the same age as these evaporite deposits being formed in California, is the same age as these shale deposits being formed in Michigan, right? How do we know that? So different depositional environments in different places deposit different kinds of sediment and produce different kinds of rocks. So how do we figure out which rocks are the same age, right? Because the coal beds that are being formed right now in Louisiana are going to be the same age as the evaporite deposits that are being formed right now in California, and going to be the same age as the shale deposits that are being formed right now in Michigan. So how do we know? How do we realize they're all the same age? So we're going to see, whoops, I got all messed up here, but we're going to see that the answer to that is from fossils. So the next lecture, we're going to get into kind of the nitty-gritty of fossils and how we do something called correlation, in which we correlate the different fossil assemblages so that we can match up different rocks that are of the same age. Okay, so we're all going to do that through fossils. So that's going to be next lecture. I hope you enjoyed this one, and I will talk to you soon next time. Oops.